Um, Great. So thank you everyone for joining. Welcome to the EMO Colloquium series of 2026. We're very excited today to have Juba, Ziani, and Sanmay who are going to tell us about their work on fixed points and stochastic meritocracies, a long-term perspective. I just want to highlight that Juba and Sanmay have been part of and participating with the EMO and EMO adjacent community and working on these problems and are working also on the creation of a new working group on education topics. So if you're interested in the topic of this research, but also more broadly about education research and intersection with algorithms, mechanism design, and computation, feel free to reach out. It's a pretty exciting area where there's a lot of exciting research questions. And as they'll tell us more during this presentation, there's opportunities for collaboration and interaction with practitioners to understand what are the core questions and how can we help from academia to solve some of those issues. Now, without further ado, I'll pass the word to Juba and Sanmay. Again, thank you so much for agreeing to participate and for sharing your work with us. We're super excited to have you here.
Yeah, thanks a lot for the introduction. And so, yeah, one thing that I wanted to say super quickly about this potential working group. So it's something that Jordan Abbott, who's at New America, and me, and I have been talking about. And we really kind of want to try to make this a pipeline between research and practice. And we want to be able to keep doing the kind of research that IMO has been doing on education, but really kind of inform practice through that collaboration. So let us know if you're interested, and feel free to shoot me an email. We also are trying to gauge interests right now in this working group. But anyway, so now let me go back to the research and the paper. So this is with Gaurav Pokhariel and Divyangsu Sen, who are students, and Sanmay Das, who's here, and myself. And so basically, we're interested in looking at feedback loops that come in processes that involve admissions, like, for example, university admissions to college admissions. And the idea, but you could think of other types of feedback loops. But the idea is to try to understand this kind of phenomena where the rich get richer. And if you start, you maybe have two different groups, and you have a group that's slightly advantaged and a group that's slightly disadvantaged. And those groups are going to be more sharply advantaged and disadvantaged over time. Um, in the context of education, really what we're trying to say is, and what we're trying to see is understand how today's admissions are going to shape tomorrow's qualifications. Um, and so we're going to introduce a model in which basically if you're, able to get into college, if you have access to college, it's likely that in the next generation, you're also going to have a higher probability of having the resources for and being qualified for college. We're going to model this in our model, and I'll get back to this in the next slide, as having what we're going to call high type, and we're going to call a high type someone that's clearly qualified for college in the setting. And what's going to happen is we want to see this feedback loop, which is saying that basically a population that has more high types will actually get more admissions from college. And then those, we want to show that potentially even very small initial or no initial differences at all can start compounding over generations. And there is a lot of work that have been thinking about fairness across different populations, and that has been thinking about also feedback loops. And in the space of fairness and decision making, I want to highlight some of the very seminal works in this space. So there's the original work of Dwork et al., which is fairness and awareness. There is the work of Hart et al. And the works of Friedler et al. And so Dwork originally is introducing the idea of group and individual fairness notions. Hart et al. Is introducing new fairness metrics, like equalized odds that are very widely used in practice now. Friedler et al. Was also looking at individual and meritocratic notions of fairness, trying to understand when they're possible and impossible to obtain. There's also been some work highlighting that some of those definitions of fairness, especially ones that are more individual meritocratic, they can be hard to obtain. And they can be hard to obtain because it's hard to get a very accurate measurement of someone's qualifications. And if you get the measurement wrong and you make wrong decisions based on the wrong measurements, you're going to have issues with fairness. One area that's related is in the role of stochasticity in fairness, and we'll see that like stochasticity is going to be actually a very huge part of our model and the main insights that are going to come out of this paper. There's also work on performative prediction, which is also what happens when you can like see distribution shifts over time. So the way you design your rule and your emission rule is going to shift populations, and that's going to be another effect that we're going to observe in our paper. But really, the most significant connections here are going to be all of the works that are on dynamic fairness and like feedback loops fairness. And there is a few of those that I want to highlight. The first one is Liu et al. From 2018 that basically shows how fairness constraint can actually have an like unfair long-term outcomes due to feedback loops. And they're really now starting to take the long-term into account. And in that paper, they only do like a one-step feedback loop in which groups have like different selection rates, but that's going to already highlight like long-term fairness in like the second step. There is the work of Baek et al. That looks at feedback loops in the context of statistical discrimination and how that has an effect on hiring. And so basically what's going to happen is like the groups are going to be asymmetric in the initial evaluation of a firm that's trying to hire them. And that's kind of like asymmetry is going to reinforce over time. And the reason for this is that if you're hiring more from a group, you have more information about this group and you want to keep hiring more from this group. And this is really the main effect in this paper. Finally, there's a few papers, Huan Chen, Kleinberg et al. In 2021, and Acharya et al., which is actually one of my papers. And Krishna is my student who just finished his PhD. That's looking at like intergenerational mobility in resource allocation. And the idea here is there's going to be some form of initial disparity in how resources are going to be allocated to different populations. And populations that have more resources will do better and be able to accumulate more resources. And such a feedback loop is going to form. This is really studying those rich get richer effects. And in this case, we're studying interventions. All three papers are studying interventions that actually have a long-term impact and are kind of like taking the long-term structure into account. So now I want to highlight that what I'm going to talk about today is different from all of those works. And it's going to be different from all of those works because even though we're looking at how unfairness is going to arise in the long term, we're going to assume that there is absolutely no difference between our populations in any way. And we are going to start with populations that are perfectly symmetrical. We are going to assume that at every time step and every day, allocations are going to be fair and meritocratic. And we will show that even in this case, where populations are the same, everything is fair in the sense of a single time step, unfairness is going to arise. And I want to highlight why, but the answer is going to be randomness in itself can create disparities across different populations that then are going to self-reinforce. So here is roughly what our model is looking like. So we have two populations. I'm going to call them Group A and Group B. We want to make the model as simple as possible. And remember, I want to tell you that disparities are arising even if populations are completely the same. So I'm going to say that Group A and Group B, they have the same number of individuals. We're not even going to take into account the impact of having like disparities in size. So this is already an ideal world. And we have a college that has a capacity of 2 alpha, and the students in Group A and Group B are going to try to be admitted to college. The reason we're using 2 alpha is because you ideally, in an optimal world that is completely fair, you want an alpha fraction of Group A and an alpha fraction of Group B to be admitted to college. And so this is why we have these 2 alpha instead of alpha. But like, yeah, so it's a tiny bit weird, but it will come clear later on why it matters. So now we have admissions to college that has a capacity of 2 alpha, and the capacity is shared between Group A and Group B. And all of the admissions are going to be fully meritocratic in our setting. I'll give a tiny bit more information about what meritocratic means in this case. But then what's going to happen is like, okay, so students here, they're going to get into college. And who gets into college is going to determine the type around T+1. And so students effectively that are going to be admitted to college they're going to have a higher probability of remaining a high type in the next round. And you can think of the next round being the next generation. So this is roughly how this is going to work. For a student has not admitted to college, this is what's going to happen. So we're going to assume that our students can only have two types that are low types and high types. And actually, sorry, forgot to say that initially the populations are completely equal. So they have the same distribution of high types and low types. And the high types are qualified students, low types are students that are less qualified. Um, so if you look at the students that are not admitted to college, we're going to make a few splitting assumptions, but we're going to say that there's a stochastic transition from their current type to the type that their, say, descendants are going to have in the next round. And we're going to say that if the student is a low type and doesn't get access to college, they will remain a low type no matter what. Students that are a high type, they can remain high type in the next round, but this is only happening in some probability Q, and if they don't get education, they're not admitted to college, that type can degrade over time. And with some smaller probability 1 minus Q, a high type might actually become a low type in the next round. Now, if someone is admitted to college, there is a difference, and this comes in two ways. The first one is you can see what's happening to the low types here is very different. Because now, if a low type is actually admitted to college, they now have a probability of becoming a high type. And we're going to denote this probability P. We're going to assume generally that P is larger than Q, basically saying, like, denoting the high impact of college education here. So with probability P, they're going to be a high type in next generation. And with probability 1 minus P, even though they go to college, there's still a chance they're not going to be a high type, they're going to remain a low type. The high types, they're also going to stay a high type with probability P, but there is a chance that even though they go to college, they're also going to become a low type. This P, again, to keep things as simple as possible and to make the model as simple as possible, and really to just isolate the effects of stochasticity, we're going to assume this probability is the same. The only assumption we're making here is P is bigger than Q. And that kind of makes sense. If you're a high type in college, you should have a higher probability of remaining high type than if you're high type non-college. So this is the part where the resource allocation really matters. So does that make sense to people so far? Cool. So I'm guessing that means there is no question so far. So I've been relatively clear. Good. So now I promised you that at every time step, in every generation, we're going to actually have a fair and meritocratic admission rule. What does that mean? Well, we're actually going to show that there is a unique rule that satisfies three things. So it's meritocratic, which means that like the high types must have a higher probability than the low types of actually going to college. It's going to be fair in the traditional sense of equalized odds, and it's going to be efficient in that every seat in college is filled. So you're actually going to fill your capacity. And if you impose those three very natural constraints, we'll see that there is a unique rule that actually works here. And the rule, what it does is if there are more qualified students than the college capacity, we're going to call this the oversubscribed regime. And there we're going to admit high types proportional to the number of high type in each group. So a group that has more high types will get more people into college. And this is effectively equalized odds because this means that no matter what population you're in, your probability of going to college as a high type is the same. There is now also an undersubscribed regime because you can imagine where we will have situations where there are fewer qualified students, very qualified students than the actual college capacity. In this case, we're going to admit every single high type, but we're going to make sure that we split the remaining seats proportionally to the low types. And again, that's equalized odds because the low types have the same probability of getting into college no matter which group they're in. So that definition is like relatively natural. And if you think about this, we're doing the really fair thing at every time step. This is the best case for fairness. We never do anything unfair based on the current composition of low types and high types. And I told you before that, okay, something weird happened. This is weird, right? Because everything is completely symmetric and everything is completely fair. But yet, fairness at each time step is not going to be enough here. And the reasons for this is going to be, okay, what if one group for some reason gets slightly ahead? For some reason, they manage to get more high types than the others. Then if that happens, you can imagine they have more high types, and more high types leads to more admissions leads to more high types leads to more admissions in this population, and that creates a feedback loop. But why would that feedback loop actually start? Because the groups initially I told you are completely the same. Well, what actually happens is like there is randomness in the transitions, if you remember. And that randomness in the transitions can actually create disparities and make artificially one group better than the other after even one time step. This is really where this is going to come from. And so I want in like what we're going to do in most of this talk is to explain exactly how this randomness is going to impact admissions in the long term and the types of students in the long term. So in part one of the talk, I'm going to assume that Sanmay, do you want to say something?
Yeah, no, there was just a question about what is the definition of efficiency, which is just that all the seats have to be filled up.
All the seats are filled. You're not leaving any capacity on the table. Yeah.
Yeah.
So now we're going to assume that both groups face identical dynamics. What I mean by this is like even if one group pulls ahead and they happen to have more high types, the dynamics are the dynamics of how your type is going to update if you're not in college, and the dynamics of how your type is going to update if you're in college, they're going to still be independent of your group, even if one group becomes more advantaged. So the group is still facing completely identical dynamics in terms of like how they update from one round to the next. This is really what I mean here. And so this is basically what I already told you in the model, but like non-admits that are high type retain their high type in some small probability Q. Non-admits that are low type or high type, they will become high type with probability P, and non-admits that are low type will stay low type. No group here has any preferential treatment. This is true for group A, this is true for group B. Transitions are exactly as I described before here. So just to remind you super quickly, this is like basically what it looks like. So how are we going to analyze this problem? Well, this is a stochastic system, and so there's a lot of randomness involved, so it's going to be a bit weird to analyze, but we're going to actually do two different things here. And one is going to look at fixed points. But what we call a fixed points here is going to be in an average sense. We're going to really look at the average system behavior. So this is going to be a deterministic notion here. This is going to be a deterministic notion when where we're assuming we're basically computing the populations in expectation, like the number of high types and low types are going to be in the population expectation, and try to understand the fixed points of this expected dynamics. Those fixed points in practice, they can be unstable because even if in average and even at some point you converge to those fixed points, the dynamics can kick again, and people can move again away from those fixed points. So we're also going to have a stochastic analysis, which is going to encode that variance over time, and that's going to actually show that we have cycles of like moving away and back to those fixed points that are they're attractive, but it's hard to stay at them. Before I tell you about two, let me give you the main result for one, which is about the average system behavior. And so in our model, we're going to see that there is only a single fixed point. And this single fixed point is actually really nice for us because what does it say? It says that xa is equal to xb is equal to alpha p. So let me explain what all those things mean. But xa is the fraction of people in group A that are high types. XB is the fraction of people in group B that are high types. And we're basically saying that the fixed points of our dynamics is like the two populations are completely symmetric and equal. So we haven't created one population that's much better than another population just because of randomness in this case. Remember, this is again in a very average sense. Then this alpha P is basically, remember that alpha is actually half the college capacity. And P is the probability you remain a high type. So the number of highly qualified students that you will get will be less than the college capacity. So the college is going to have some spare capacity for some low types at equilibrium. Our fixed point is going to be in what I called before the undersubscribed regime. And if you think about this, it's natural. The reason it's natural is because you cannot keep the capacity at high type, because at every time step, some of the high types, even if they go to college, they actually become low types. And the fraction of them you actually keep is roughly P. Each group is going to have exactly half the college seats in this case. So yeah, perfect. We have parity. This is exactly what we wanted. And so the groups, and no matter what you start, at some point, the groups are going to reach parity. It might take some time, but you can start like something uneven, and like one group has more high types than the others. Eventually, you will come back to a point where they both have alpha P, and you have parity across the two groups. It looks something like this. So here we have two figures basically showing how long it takes to go back from a starting point in which the populations are different and very different in composition to actual parity. And so here you can see that like one population has this very small fraction of high types, it's only 0.1. One population has like a much higher fraction of high types, it's 0.7 here. We do this in the oversubscribed and the undersubscribed regime. In the oversubscribed regime, there is a huge number of high types, so you're basically saying number of high types is bigger than the college capacity. Here, there's a much smaller number of high types, and the number of high types is kind of like smaller than the college capacity. And then those populations start apart, but eventually you see that they converge to here 0.27, and that's exactly alpha P in this setting. Here we picked the probability to maintain your high type to be 0.9 if you go to college. We picked the probability of remaining a high type if you don't go to college to be 0.40, and alpha is 0.30, and so alpha P is 0.30 times 0.90, and you'll get 0.27. So exactly what we claimed in the theory. So now, that was the good news, but I'm going to tell you the bad news. We're going to have temporary disparities in the system that are due to the randomness and the stochasticity. Even though theorem 2 is saying that our groups are going to converge in average sense, the stochasticity is actually going to imply that our system is not going to always stay at parity, and the groups are going to separate, and they're going to return to parity and separate again and return to parity and separate again and return to parity in a cyclic way. And this is what's going to happen here. And the question we're asking is we want to understand how bad this can get and how long the separation, for example, is going to last once groups start separating. This is going to look something like this. And I think like a good example of like this cycle happening is right here. You can see that at this point, the two populations are exactly the same. But then here, group A, the blue population pulls ahead, and they pull ahead for several generations, and then eventually we actually go back to parity. And then again, it crosses again with like group B. Which group takes the advantage can actually switch over time if you run this for like enough generations. And here you'll see that like sometimes group A is better, sometimes group B is better. One thing that I want to mention is this doesn't look like that much of a separation, but if you think about the order of magnitude here, well, the college capacity is like 30% of the population size, and this is a good difference by like maybe 5%. This is not negligible. In the context of this capacity, this is actually significant. So the way we're going to measure this more carefully, and I'll give you a few more statistics about this very soon, is we're going to introduce the separation, the concept of separation, and separation is very simple. It's just the difference in the fraction of high types in population A and high types in population B. Remember that like the number of high types, or the fraction, sorry, of high types in the population is our measure of how well that population is doing. We want that separation to be as small as possible. That means that the groups are reaching parity again, and there is no difference between them. So we want delta t to be close to 0. And so now let me show you actually what delta t looks like in practice as a function of the size of the groups. So here, what I'm plotting is on the x-axis, I'm going to plot the size of a group n. And here it's going from like a low value of just 10 to about 1,000. On the Y-axis, I'm going to show you the expected value of the maximum level of separation that happens over 100 time steps. So it's like really in expectation, how bad can things get in a controlled window of 100 generations? And the answer is actually quite bad, especially for lower values of n. Because if you look, for example, on these different curves, so different colors correspond to different college capacity. And the red curve is like the smallest college capacity, the green curve is like the highest college capacity that we have so far. But if you look at the red, for example, the college capacity is 0.1. So remember, sorry, alpha is 0.1. So total college capacity is 0.2 effectively. But there is different ways you can obtain this 0.2. You can get 0.1 from population A and 0.1 from population B. The worst case is you can get 0.2 in population A and 0 in population B. And that would lead to a separation of like 0.2. So really, if you put this in context, the worst case is 0.2. And here we have a separation of like roughly 0.1. In some setting, and because of randomness, it can actually sometimes be even a bit higher. This is a significant amount of separation given that the actual capacity is 0.2, if you think about this. This attenuates a bit when you have bigger values, because here, the maximum separation can be 1, and so like the impact is like slightly lessened. And one thing that's also important to notice is like as your group sizes are becoming bigger, these effects start disappearing. That's normal. Again, all of our insights are coming from the stochasticity. If you take n to go to infinity, there's no stochasticity anymore. You have effectively just fully deterministic dynamics. So at some point, those effects are going to go. But those regimes are non-trivial, right? 10 to 100 could be a cohort of students that are trying to get a job somewhere, or it could be trying to get a selective internship. It could be athletes that are applying for a football team, and some of them just happens to be because they were born later in the year, which is completely random, end up being left behind. So those are not insignificant group sizes. They can have very, very significant effects in real life. Okay, then I want to tell you something about, okay, so this is the worst case. This is the kind of like worst separation that can happen. But the question now is like, well, once that separation happens, once we're far apart, I have argued to you that eventually you go back to parity. So the question is like, how long is that going to take? This is a very ugly theorem. Don't pay too much attention to it. I'll explain in a second what this means. But you're going to start from like basically some initial separation we're going to call delta 0. So imagine we just reset time. Whenever separation happens, I'm saying this is time step number 0. And we're saying that separation is kind of like big enough. We have a separation of the order of eta. Question is like, how long does it take us for the separation to become like very, very like to go below a certain threshold? This is given by this 2 of eta. Eta here is the threshold, the target threshold. Say once people are willing, like once the two groups are within eta of each other, we have achieved the level of non-separation that we wanted. We went back to parity. This is our level of parity effectively. The first thing to see is that this T of eta is going to increase with P. And that makes sense. P is how much of an impact the college is going to have on students. The higher the P, the more students that go to college are likely to stay high types in the next generation. So in this case, you have a more effective college, and then it becomes harder to correct for accumulated advantage. It's going to decrease with like the initial separation delta 0, right? I mean, the more separation you have, the harder it is going to be to overcome that separation. And yeah. But one thing that's actually important to note is we actually see it's kind of like hidden in the formula of like what the F looks like, this F of alpha, picture and everything. But we actually have like a very, very negligible effect in terms of Q. And this is kind of like interesting. And we're basically saying that this doesn't really have an effect in practice. And in theory, too, and like the idea is like basically a return to parity requires going back to the undersubscribed regime, right? This is what I argued in the first theorem. And once you go back to the undersubscribed regime, well, all of the high types actually get to go to college. So that Q is not really kicking in anymore. So to go back, I kind of like already mentioned this actually because I forgot I had this slide. But the when we see that like the stochasticity is going to be really important like in a smaller n regime, and like I gave you some of those motivations, but like another motivation is not just athletics or hiring for fellowships and internships, but also like promotions. If you're thinking about like a company and you decide who's getting promoted, or an academic department of size, maybe it's small, maybe it's 50 people, maybe it's even smaller than this. Randomness on who gets early awards, early promotions can have a really huge and like long-term impact on people's careers, if you think about it. But anyway, I'm almost done with part number one. Um, but the punchline is like, even when everything is completely fair, meritocratic and efficient at any given time step, and even when the population starts exactly the same, unfairness can still happen in the short run. And parity is a fixed point, but it's not a stable end state. Groups will drift apart and come back to parity. And so I'd say something really important in how we should think about fairness. Because often when we think about long-term fairness, we say, okay, at some time step, we'll reach demographic parity. We're done. We're good. But that's not true here. We're showing that this is not true. You reach demographic parity, well, you might just go back to an ideal starting point, but then you might separate again from there. So just saying there is some time horizon after which you achieve demographic parity is not going to be sufficient. And I think it's probably one of the most important insights here. And now what I'm going to do is I'm actually going to let Sanmay give the rest of the talk, and he's going to talk about actually what leads those disparities to actually persist in practice in the long term.
All right. Hopefully everyone can hear me fine. So thanks, Juba, for setting this up so well. So I want to take like the next somewhere between 10 and 15 minutes, just tell you like a couple more things, right? And so the first of these is, you know, let's try to model something that we believe exists in the real world on top of this stylized model that we've built so far to understand what effects that is going to have on the population, right? So so we're going to call this the model of affinity advantage. And let me see. Okay. I can't see the participants anymore, so if anyone has something to say, just like, unmute and chime in or something. So we're going to make one small change to the model over here, right? What we're going to say is, okay, suppose one group has more high types than the other groups at a particular point in time. All right, so all we need is for one group to have somewhat more high types than the other group. We assume that this gives all of the members of that group who are not admitted to college a small extra boost epsilon in their probability of remaining a high type, which is greater than zero or becoming a high type. Okay, so why are we doing this particular model? Well, it's in fact the simplest model that we can think of network effects, which are a well-known thing throughout the social science literature, right? So we've seen things like, for example, in-group hiring, people are more likely to hire from their networks or their socio-demographic groups. The visibility that is gained from being from the same group, social capital that's accumulated, and so on and so forth. So we assume that it gives a tiny potential advantage. Well, the value of epsilon can vary, but we can think about this as giving sort of a small extra advantage to those who are in group, do not make it to college, and by in group I mean part of the group that happens to be in the majority at this particular point in time. Everything else stays exactly identical to what it was in the equal advantage model. Okay? So we're coming from the same starting point, and what we're going to tell you about now is that we end up with completely different kinds of outcomes in this case. So in this graph over here, what we've got on both of these is that we've got the generation on the x-axis, and again, the fraction of high types in each group on the y-axis. For a particular instantiation of this, so this is with 200, with n is equal to 200, the efficacy of college parameter P is 0.9, the alpha parameter is 0.3. And so the epsilon over here adds a 3 percentage point boost to the majority group at any point in time. And what we've seen before is that, like, if you don't have this affinity advantage in the equal advantage model, you'll see this kind of stochastic behavior where, so that's the graph on the left, where the two populations kind of move around, one crosses the other repeatedly, and so on and so forth. When you introduce the affinity advantage, something very different happens, right? One group at some point gains enough of an initial advantage that it then ends up becoming entrenched in the population. And it actually never dissipates after that, right? So in this case, what we see is that group B, even though it's like actually slightly below group A initially, it at some point gets a significant sort of, advantage in the fraction of high types in the population. And at that point, the two groups move away from each other and they stay moved away from each other, right? They're actually sort of going to converge to a point where they are not going to come back to mingling. We're going to see this sort of permanent separation in the proportion of high types in group A and group B. So that's sort of, one example from a run to give you a sense of what it's like, but we've actually been able to sort of, prove this in the paper. So we basically say with any epsilon value greater than 0, and so that means that, like, epsilon, there's no sort of minimum bound on what it has to be. As long as the leading group has a tiny advantage, the system will eventually reach a permanent non-zero separation in the long run. And you can actually, like, come up with a fairly interesting sort of statement over here, which is that there's actually a threshold, which we call epsilon tilde. If in the small epsilon regime, where epsilon is smaller than this epsilon tilde, there's going to be a permanent gap in which both groups survive in terms of they both continue to have some high types, but the separation keeps growing with a higher value of epsilon. Once you get to this value, to this threshold value, epsilon tilde, the trailing group actually ends up being completely excluded from collegiate equilibrium. So what happens in that case is that, one group initially gets an advantage. And again, these two groups are initially identical. So it could be group A or it could be group B. We don't know what that's going to actually be. But then the trailing group will eventually end up in a situation where none of its members are high types anymore. So that's kind of a stunning result in some senses that, like, adding this affinity advantage can lead to permanent gaps regardless of what the value of epsilon is. And if epsilon is particularly high, it will lead to complete exclusion of one of the groups from having any high types in this kind of situation. So this is sort of a graph that shows this result, essentially. So over here, the dashed red line is the value of epsilon tilde. Epsilon is on the x-axis, and then the y-axis is showing the separation delta between the proportion of high types in the population between the two groups. And we can basically see that it's sort of consistently growing. Once you get past the threshold, there's actually no high types left in the in group B, in the minority group. And then essentially all of this separation is because that's the proportion of high types in group A at that point in time. So it's interesting, right? So even with very, very small values of epsilon, as you can see on the left side of this graph, you do see a permanent disparity between the two groups. So even sort of small network effects of this type can have significant effects. Why is that, right? So basically, as I've been pointing out in these, right, the basic mechanism, right, the take home of this is this. At some point, stochastic fluctuation in outcomes is going to give one group a tiny random lead. The affinity advantage is then going to capture and amplify that lead over time. And so it becomes self-reinforcing and permanent, right? So this is kind of like the Matthew effect, right, which Merton identified in sort of scientists and scientists' careers, quoting from the Bible, unto everyone that hath shall be given. So the rich get richer phenomenon, basically. So does this happen in the real world? Well, we've seen plenty of evidence out there that, like, there are affinity advantages in some cases, right? So we know that, for example, universities dominate faculty. Some elite universities dominate US faculty hiring, and this can create self-reinforcing prestige networks. It's known that in the sort of labor market kinds of situations, part of the disparity in Black Americans getting hired is because they access smaller employment networks. They often don't have, it's not that they don't use their networks, it's that they don't necessarily have contacts in the places where they are applying to jobs. We might see similar things happening in the world of algorithmic monoculture, where similar systems deployed across domains could end up specializing on favored groups, which is the same sort of feedback loop that our model is predicting over here. So the basic point over here is that the smallest network effect can lock in a permanent group advantage, right? So this is a combination of a phenomenon that we saw in the first model, the equal advantage model, which is that stochastic fluctuations will eventually lead for certain, semi-persistent periods of time to one group looking like it has an advantage over the other one. And then if you throw the affinity advantage in on top of that, that advantage becomes real and locked in over a long period of time. In fact, it's going to stay sort of permanently higher in this kind of a case. So this is kind of worrying, and the whole point of this paper is to raise this issue and to think about, like, what can we do about the fact that, everything starts off equal, or if things don't start off equal, if you have equal advantage, you think that they will eventually reach equality, but you introduce sort of, some small sort of lack of robustness in the system that can arise through things like these network effects, and you can end up in a situation where certain advantages get entrenched over time, and one group could be permanently disadvantaged. So this is a very stylized model, right? I want to talk very quickly through what happens when we go to a somewhat more complex model, and then open it up for questions after that, right? So we actually looked at saying, okay, what if we're still going to be in the world of models because we're doing models over here, but let's consider a richer model where we don't just have high types and low types and these probabilities P and Q. Let's instead have continuous abilities. So now we're going to have abilities modeled as being from a Gaussian. The groups are identical at t is equal to 0. I'm not going to go into like too much detail, but the basic qualitative ideas are the same, right? The college is going to admit the top alpha fraction of the population by standardized ability. Ability is then going to evolve over time, right? So what do we have? We have the ability at time t plus 1, which is the next generation's ability, if you want to think about it that way, is the ability that you had at time t, plus there's a small boost there's an ability boost, not necessarily small, from going to college, which is only for those who are admitted to college. There is an affinity advantage with some mean mu epsilon, which is only for those not admitted to college and in the majority group, plus a noise term, right? So this makes the population distribution a little more realistic than just having high types and low types. So same basic mechanisms. Now we have continuous abilities, continuous college boost, continuous noise, and the admissions model becomes on the continuous ability spectrum. So you set it so the college sets a threshold there. What do we see happening over here? We see something very similar happening, which is that the ability distributions diverge over time when an affinity advantage exists. So the panels on the left are showing you what happens between time 1 and time 99 across the two populations. So group A is the blue population, group B is the kind of yellow orangey population, and the darker part is both groups together, right? You can see that the overall population distribution of abilities is changing because of the effects of college between time 1 and time 99. But if you look at the left graph, there's no significant change in the difference between the two populations over time. Whereas if you look at the right graph, group B at some point is becoming favored over here and is going far out to the right tail of abilities compared to group A, which gets left very much on the left tail as time goes on. So this is documenting very much the same effect that we had in the stylized kind of two-type model, in an example where we have a sort of more realistic distributions, realistic distribution of abilities and impacts of college and noise and so on and so forth. In fact, what happens at different values of this mu epsilon, we can see that the share of admissions to college can change fairly dramatically, even with pretty low values of mu epsilon over here, right? So at a value of 0.06, and remember the baseline over here is that we have a standard normal distribution, 60% of the advantage group is is constituting sort of the admissions to college. And once you get to 0.24 for mu epsilon, which again, keep in mind is less than a quarter of a standard deviation here, you have more than 0.7 in this particular case, right? So what happens if you have higher capacities? We see that in those, it typically attenuates but does not eliminate the separation between the populations. So what is this showing? It's basically showing that these results are robust, right? We've done various different experiments that are in the paper. So if you have so we do robustness checks on the college efficacy, which is the p value in this case in the original model, right? In this case, it becomes this term theta times IJT, which is the ability boost from college. If you have sort of higher college efficacy, that boost is higher. It slightly dampens the separation, but it doesn't eliminate it. For noise, it's kind of interesting. It's non-monotonic because the separation actually peaks at intermediate levels of noise, and this noise is modeling sort of, how efficient is the intergenerational transmission of ability. So separation is a robust feature of the dynamics of this model. We see it in various ablations of this sort of more complex model. We've seen it in the theory in the simpler model, and we see that this kind of separation appears to happen kind of regardless of the specific choices that one ends up making. So what does all this mean, right? It means that at the end of the day, right, we have to think about this as a dynamic problem. Just because you get back to parity at some point in time does not mean you're done. You cannot think about auditing fairness in a static manner. You have to think about sort of, what's going to happen over time. Randomness in pipelines, right, including in things like using machine learning for admissions decisions or employment decisions or any of these kinds of things, could itself end up driving group disparities, even if you've got the fairest of fair rules for doing admissions. And finally, network effects are a huge deal. Even really small sort of network effects in terms of like, a preference for giving people opportunities. In this case, even if they didn't go to college, right, that's where we've modeled it happening as the simplest thing. But obviously, this would be even stronger if the network effect also applied to those who went to college. And that is the key mechanism here for entrenching separation over time. And so we need to think about ways to actively counter these kinds of network effects in the provision of opportunities to become and remain high type. Finally, we talk a lot about expanding capacity and access to education. And over here, I think one of the messages that we've got over here is that yes, it can help, right? You increase the capacities that can sort of, attenuate these things, but it is not a fix in and of itself of everything, right? There are other more fundamental problems which are not fixed by this. And expanding capacity is not going to be the be all and end all solution to these problems. So finally, just to summarize sort of our main results, you have for the stage game, right, for the one stage thing that's happening, if you have a fair and meritocratic rule, that does not mean that you're going to get long-term fairness. You will get cyclical disparities in these cases. And so you take a snapshot at any point in time, you may well be in an unequal situation. Stochasticity causes this temporary separation, which causes groups to drift apart and return to parity. Any epsilon greater than 0, which is the affinity advantage, leads to a permanent separation between the populations, right? It doesn't have to be big enough. You'll always see some separation from any network effect advantage of this kind. And if it's large enough, you will actually see complete exclusion of the group that initially somehow loses out on the advantage. So, a couple of things in terms of like what can one think about doing as follow-ons from this kind of research. So the first question is just, okay, so we've documented these ideas in kind of a number of models at this point. How can one intervene, right? What can we actually do to improve systems? And then can we actually characterize the long run harm of doing one-shot fairness interventions versus fairness interventions that stay ongoing, which is a particularly sort of, apt point in the US at this moment when we think about the history of what's happened with the Voting Rights Act, for example. So all kinds of interesting questions coming up in this area. We hope that this particular kind of model will be a useful model for people to start from in order to take this and run with it and figure out, okay, what are the interesting questions that we can examine about long run fairness as influenced by these kinds of selection processes. Thank you very much. This paper will be at FACT this year, so if you're going to be there, Gaurav will be presenting it over there. Yeah, hopefully we have time for questions.
Thank you so much, Sanmay and Juba. That was really, really interesting. I think that we have a few minutes for questions. So for the people who are in the meeting, you can leave some questions in the chat. Or I think that you should be able to also raise your hand. Maybe Sandro, if you want to help us, you can make also that people can unmute themselves if they want to ask questions. Thank you so much. So if you want to ask questions, you can just unmute yourself and raise your hand. And you can also leave further questions in the chat. I can maybe get us started. So I have a few questions and I really like the presentation. One thing that I was wondering, and if I got this wrong, please correct me, but the affinity advantage case. So when you have these network effects and this epsilon term, I guess what's happening here is that there's a higher probability by which someone who doesn't attend college but belongs to this group can get the high type in the next generation, right? And so I think that there's a subtle discussion there, right? Because in some sense, one could think that the objective could be have the largest amount of high types across the population, regardless of their group, where this epsilon term would have some positive effect, but it has this downside of creating more inequality. And I just wonder whether that's a trade-off that you're thinking about or characterizing in the model. Because I guess the conclusion that these network effects should be countered might be a bit stark when you think about it from that perspective, right?
Yeah, so that's a really good question, right? And I mean, it's a little bit so we haven't dug into this too much, right? There are other things where you actually think about this question of like so we have a separate project ongoing where we're trying to think about classroom rostering and how it affects impacts on like who ends up being who ends up basically doing better on tests in future years and how is that affected by classroom composition. And the question there is actually one that's really relevant to K through 12 school systems and that they're really interested in, which is should you be trying to sort of maximize overall achievement, number of students who like get a high pass on some kind of test, or should you be trying to minimize disparities across populations in terms of how they score over there? I think that in this model, right, it's a little bit hard to fully get a grasp on that because we have this restricted capacity and the dynamics is going to end up bringing us always to this undersubscribed regime, which is not what you would want in the long term if you were trying to maximize sort of the number of high types in the population. So I actually think that like making progress on that question might involve some of the more complex models, right? Where where we have continuous types or something like that, and then thinking about sort of, how do these types change over time? But then how realistic is that? So we actually had some models where like, just values keep going up and up and up. And so you'd really need to think carefully about how to calibrate those models to get at those questions. So there's an interesting modeling question there as well. I don't know if Juba has further thoughts on that.
No, I think that covers basically everything that I could have said at this point.
Yeah, thanks, Annie. Thanks, Juba. I think that so Austin had a question. It's good to see you, Austin. Any thoughts of efficiency as whether the average skill is lower with the affinity advantage? I guess it kind of falls on the same direction of how do we think about efficiency more broadly in this model? I was saying if you want to complement, feel free to unmute yourself. I don't know if guys want to talk about that a little bit more.
Yeah. I think my answer to this is similar, right? In that I think you need to move to the more complex model to actually capture this question of efficiency. So I think there's a modeling question there. And this question of how to capture that in a model is actually a really interesting one. I'd be happy to talk about how to work on that.
No, yeah, Augustin, I think that's interesting, and it's not explicitly in our model right now, right? Because we're basically the fraction of high types kind of like doesn't really change. It's how it's allocated across the different populations. That is really the main effect here. But I think it would be interesting what you're saying is like there's no static effects. They might actually be lowering the average type too, and I think it'd be interesting to look at. But we don't have this in the current model. Happy to chat more about this.
I mean, it's also related in some ways to this question of like, what makes people happy, right? And all of this stuff of like, oh, everything is getting better, but if your neighbor is doing better than you still think you're doing badly. And is that and that's a little bit more, yeah, of what our model successfully captures, I think. But I think it would be actually interesting to figure out this question of like, what is actually going on with actual improvement in skills or efficiency or whatever the case may be. And then there's a question about more than two groups. I don't see any in principle problem there, right? I mean, I think the main thing that we're trying to do here is just illustrate the phenomenon, so we don't need more than two groups. I think that I don't see any problem in principle with extending this model to more than two groups.
Yeah, I don't think it changes the main insights overall. I don't see kind of like a fundamental mathematical difference. The randomness is going to be such like one of those groups is just going to happen to be the best. But yeah, one thing that I wanted to say about this is I think the results are more powerful because we're showing this already happens with only two groups. You
Yeah,
don't need to have a very large number of groups for those disparities to even start happening.
yeah.
Makes sense. Um, so there's still maybe 2 more minutes in case someone else wants to throw in another question. I know that I definitely have more, but I'll just wait 30 seconds to see if someone wants to jump in, and otherwise I'll keep one.
I want to very quickly say this is Gaurav and Sen were the grad students who worked on this. They're both here. They're both awesome. They both do like really great work, and you should talk to them when you can.
Yeah.
So, I mean, if there are no other questions, I'm happy to throw in one more, which is something that I also was thinking about in a different context of resource allocation into like natural resources, which I guess there's a fundamental tension between, what you mentioned as like short-term fairness and maybe long-term fairness, right? You mentioned very clearly that there's this unique rule that satisfies fairness, meritocracy, and efficiency. And when you use that rule, you run into these unfair cycles, even when things are starting off very leveled. I wonder if you have given some thought into how to trade off these two quantities, right? So what's sort of like a principled approach to say, okay, this much amount of short-term unfairness is tolerable to reduce the long-term unfairness? Is there sort of like a Pareto frontier between these two things? And is there a way to think about that in a principled way in your model?
So what I would say about this is like I mean it's related to the papers that I sent you in the chat, right? But there's a couple things here. Thing number one is there are papers that show that short-term interventions that are not fair, as you said in the chat, actually kind of like they're not fair in our sense, actually work really well on the long term. And one such intervention that people have looked at is affirmative action. And when I'm saying not fair, it's like it's not fair in the sense of our definition, but actually there's two papers. There's the Muzanar et al. And there's a paper by Hoda Heydari and John Kleinberg that are kind of like showing how that intervention is actually helping you with reestablishing fairness in the long term. Um, the thing that might be not great about this is like affirmative action is pretty controversial, and some people will tell you this is very unfair because this population of very highly qualified applicants is not getting their due diligence. I don't think I know right now of a work that tries to do something smoother that's kind of like in between, like a very sharp intervention that really kind of like tries to equalize the populations very fast. But I think it's super interesting. Like the design, if like you have some maybe kind of like objective that takes into account the both the benefits but also the harm in like some discounted manner where harms that are happening today are kind of like perceived as much worse. Maybe there's something interesting that could be done. I don't think I know of something doing this at this moment.
Perfect. Thank you so much for that answer. There's one more question in the chat. I do want to be mindful of people's time, so we're already 1 minute past one. So if you have to head out, of course, go ahead and do it. And thank you so much again for joining. Juba, Sanmay, do you have a few more minutes to take the last question?
Sure.
Great. So it's right there in the chat, right, Charlie? If you
Yeah, I
want
see
to,
it. I see
yeah.
it. I mean, so my take on this would be, right, there's some things that are interesting there, right? So what one I mean, at some level, you could think about doing some kind of like reverse redlining kind of thing, right? So you have some like, factors X that you know about, and you have some sort of, ability thing, and then can you then make decisions that are in some way based on X rather than just ability in order to make the decisions, and that might help you to. So there's definitely ways in which you can use if it's permitted, right, to use external knowledge about the population to in some way try to balance outcomes. So that's definitely a possibility. It's not something that we are doing in this research, but that's something that people have thought about. Whether, I mean, the issue to some extent, right, which that runs into is just this question of like, is that meritocratic? you know, I could actually make arguments that in many real situations it is, right? Because like what you care about is not necessarily past achievement, you care about future fit, and there may be other things that like help to do that. But I think that like, this formulation where you have that is a cleaner version of kind of the true dilemma. And so I definitely think that in terms of interventions, right, introducing, let's say, a feature vector X, it could just be one variable or something like that, in addition to the ability and trying to think about how would you use that feature vector to do your to do your stage interventions, is definitely a useful direction. And Juba may have more thoughts on this also.
I don't have to. I actually don't have any more thoughts. Just because, to be completely honest, I understand the theory landscape here a lot better, and I understand the practical studies on this. But yeah.
Yeah.
Okay, thank you so much, guys. I think that we can start wrapping up the session. I want to thank you one more time for presenting, for sharing with us your work. Really fascinating stuff. To the people who are still here, a reminder that you and Sanmay are starting this working group, this reading group about education problems. So if you're excited about these type of questions, feel free to reach out. And we're gonna have the final session of the Emo Colloquium series in 2 weeks from now. We'll post the announcements on the relevant websites. Again, thank you so much, guys, for your time. And to everyone, have a great rest of your day.
Thanks for having us. This was really great.
Yeah, thanks for having us.